we are considering different applications of continuity equation by demonstrating, by exercising, or carrying out some examples, solving some examples of continuity equation. And in this context, now we consider a two-dimensional flow situation, and we see how the flow field looks like. We look at the question, the example that is there is we consider the velocity field such that it is unsteady and it is given by the vector v, which has components u and v, such that the u component is 0.5 plus 0.8x in the x direction and 1.5 plus 2.5 sine omega t minus 0.8y in the y direction, and where the omega is angular frequency and it's equal to 2 pi radians per second. We need to verify that this fluid flow can be approximated as incompressible. So this relatively is a simple problem, and all we have to do is to see that it satisfies the continuity equation in two dimensions, which is du by dx plus dv by dy equal to 0. So that is all we need to see. And what we need to do, we take out the u component, put it in its value, we take out the y component, substitute it. If the equation is identically satisfied, we have got it that it is approximated. If it does not satisfy, we have a problem. So let's see. The components are given, as I have already stated, and one can see it very simply. They are given to us. U is 0.5 plus 0.8x and V is 1.5 plus 2.5 into sine omega t minus 0.8y. Now remember that there is a t occurring here, but if it's a steady flow, there is no t, and therefore in the continuity equation, which in two-dimensional will be du by dx plus dv by dy equal to 0, there will be no z component, and we substitute these values. The contribution from the first term will be only 0.8, and from the second term also you can see this is a constant. There is t here but nothing to do with y. So the derivative of y, if we differentiate this part with respect to y, will also be 0. And we will have minus 0.8 coming in from here, and we can see that the sum of the two will be 0, and hence the continuity equation is identically satisfied. And therefore we can observe that the continuity equation is identically satisfied for this incompressible motion and for the given condition of the flow field. I have already remarked that although t is occurring in the y component, but as far as since the motion is steady and when we take the derivative of that component with respect to y, that becomes 0. That acts as a constant and it contributes nothing.